Privileged to be here. I thank each and every one of you. So let's dwell into session. I try to share my screen. Is my screen is visible, Professor?
Yes, sir.
Okay. Okay. So I welcome you all for this wonderful series. Today we're going to cover about digital logic design in the series of quantum technology sponsored by Andhra Pradesh State Council of Higher Education. So basics on microprocessor. Okay, so microprocessor is a small device which have revolutionized our entire world. Take an example of a cell phone, internet, rapid advances in medicine. Each and everything what you're going to look at nearby you is everything is built upon microprocessor. Okay, your smartwatch. In the same way, the semiconductor industry has grown from $21 billion from 1985 to $755 billion in 2025. So the dynamic of economy always changing in the technological aspects. So whenever technology leads, dynamic shift will happen. So if you're asking in 90 is the dominant field, industrial revolution. Okay, automobile is in 19th century, but 20th is entirely semiconductors. So the paradigm shift happens. Okay, the axis happens from normal to semiconductor. Okay, so whatever we are using, all these devices, all this technology related to digital. So most of the time we are using digital technology to compute and operate. Okay, it started from 1927. His name is Robert Noyce. Profoundly, he called as mayor of Silicon Valley. So he is the first person. Able to build Silicon Valley. Okay, he co-founded Fairchild Semiconductor in 1957. Okay, he co-founded in 68, and he co-founded Integrated Circuit. So which is normally called IC. Okay, so whatever the device we are using, our computer, laptop, cell phone, smartwatch, each and everything contains integrated circuit. Okay, in the same era in 1929, Gordon Moore also evolved. Okay, he co-founded Intel in 1968 with Robert Noyce. Okay, so if you take all this industry all these so technology course they will ripe out all benefits. Okay, so in yesterday's lecture we covered about Moore's law. So Moore's law is the number of transistor on a computer chip doubles every year. Suppose in 2023 if you have 50 computer chips, or you can say transistors, if you have 50 transistor chip, so this is the computer chip, imagine like that. Okay, 25 in 2025, 2 years, within 2 years, what is supposed to get? You need to increase the double the number of transistors. Okay, so this is his law. He predicted in 1968. Right? Since 1975, the transistor keep on counting each and every 2 years. So this is happening. So until right now, the scientists struggled a lot to increase number of transistor, double the number of size. Okay. So this is how you can visualize Moore's law. from 1970. So this is your IC 4004 8080. Likewise, you can see all evolution of processor. Intel 4, Intel 4 series, Pentium means 5, Pentium 4, Pentium 2, dual core, and we ended in Intel i9. So each and every year, the transistor will get powerful processor will evolve. Okay, if you compare the same phenomena in automobile, if you compare the same phenomenon in automobile, the same development life cycle like a computer, today Rolls-Royce would cost just $100. So still, the automobile cannot able to catch up semiconductor because of this difficulty, where semiconductor increasingly develop, exponentially develop due to Moore's law. Okay, but it never going to happen for automobile. So some field will grow linearly and exponentially. Some field, whatever you do, it won't grow that much. So they have some physical limitation. So the basic definition of a topic is always about computer architecture. Okay, so computer architecture is perspective to functional behavior of a computer. So if you want to understand computer, if you want to understand how it behaves, you need to understand computer architecture if you are a programmer, right? So normally Windows 8, Windows 7, it will contain 32-bit architecture. So Windows 10, Windows 11, it will contain 64-bit architecture. More number of bits, more computation you can do. So this is the basic idea. Okay, so few double the number, then 128-bit. So we are still waiting for 128-bit architecture. In contrast, if you're looking at computer organization, it is the internal structure of relationship which is not visible to a programmer. Take an example of physical memory. We covered yesterday. Even though it looks so much of weird, programmer need not to understand each and everything. Okay, which is not visible also programmer. So this is an internal structure. Only the hardware engineer need to take care of computer organization. But a person who know computer organization and computer architecture can able to build better efficient code. So there is always conversation happening between computer architecture and a programmer. Okay, they will discuss what are the problems existing in the hardware they want to implement in the software. Okay, so you can see growth between hardware and software, where software you can scale up to so much of levels, but hardware have some physical limitation. So always hardware tends to have, physical limitation. You cannot scale just like software. So this is the bottleneck if you want to design a powerful computer or a powerful processor. Okay, so this is the basic layout. Yesterday we discussed. So we have input output devices which will interact with your CPU, your computer. So computer contains both control unit and data path which will interact with your memory. So your processor will do all computation. It will store in memory and it will store result also. Right? Yesterday we discussed all this stuff. And this is the hierarchy of computer architecture, similarly to yesterday topic. Okay, so we have two intersections. One is software, one is hardware. So this is divided by a boundary, a virtual boundary. Okay, so above the software, you can say operating system is main. Operating system is the core for your software. Okay, operating system contains compiler and firmware. Okay, which will interact with your application. Okay, so downside, same way you can see instruction output system, which is an abstract of data path control. Again, the data path and control, which is abstract of digital design. Okay, again, the digital design is abstract of circuit design. Again, the circuit design is abstract of layout. So level by level, we try to abstract. Level by level, we try to abstract. So here you can see today's topic is about digital design. Today's topic is about digital design. To understand digital design, we need to understand all this stuff, all this basic stuff. Okay. So before understanding digital, we need to understand what is the difference between analog and digital. Okay. So analog is continuous. Analog have infinite ranges of values. Okay. So there is no definite values. It will contain infinite ranges of values, no more boundaries. Okay. So it will have more exact value, but more difficult to work with analog signal and values. Having discrete values. Okay. So digital signal also have finite range. So whatever happenings for analog, it is just contrast for digital. Okay. Here you can see infinite, here you can see just finite. So we are picking 2 as a finite range because we are picking binary logic. We are picking binary logic. So binary logic is based upon 2-level system, 2-level physical system. You can say in this way, 2-level physical system, right? So it is not exact like analog, but easier to work with. Take an example of floating point or fractional. Okay, you cannot represent as much accurately like analog, as much accurately like analog. So approximation will happen in digital signal. So here what happens? Approximation. Whenever if you want to convert any continuous signal into a discrete form, non-continuous form, you need to sacrifice something. You will miss some information. You will miss some information. Okay. Take an example of a thermostat in your room, which displays temperature of 72 degree. The analog thermometer measures the temperature, room temperature at 72.482. So if you want to store this value, okay, in a digital form, okay, you will only consider 72 and you will ignore this 3-digit accuracy. Okay, so 72 degree is more than enough for your understanding, more than enough for your operation. So this is very simple example. Okay. So analog signal can be any value, any time varying signal. So time to time it will keep on varying. Okay, so it will have minimum and maximum value, which can provide either positive or negative, and they can be periodic, repeating, or they could be non-periodic. So these are the characteristics of analog signal. And you can consider the common signal like sine wave, square wave. Okay, you can consider like analog signal. And the square wave is not digital signal because its minimum value is negative. Okay, so sometimes people will confuse with square wave, which appear to be digital. Yeah. So this is your sine wave. So sine wave have continuous variation. So it will have maximum point, it will have minimum point. So I will take pointer. It will have maximum point, it will have minimum point, and it is continuous nature. So according to time, the value keep on changing. According to time, the value keep on changing. Look at the square wave. Square wave will have a definite value for a particular duration of time. Again, it will suddenly increase. Again, it will travel. Again, it will suddenly drop. So it is not it is a continuous wave. It is a continuous wave. Okay. So even though there is so much of contrast between sine wave and square wave, but both are continuous. Okay. So signal never be in a perfect shape like sine wave and square wave. It could be any shape. It could be any shape. So here look at the shape of this wave. So it will form a pattern. This pattern will repeat. So if it is repeating, the signal tends to be periodic. If it is repeating, it tends to be periodic. Okay. So if you want to understand analog, you need to understand the basic features of analog. Okay, this is your given signal. Okay, so amplitude is signal strength. So maximum point, it's peak. Okay, downside have some peak. So from peak to peak, if you are calculating, it is a amplitude. Okay, from peak to peak. So this is for positive cycle and this is for negative cycle. If you combine both, you will get the whole amplitude for a particular signal. In the same way, you can see period. Period you can consider where signals start from your axis and it will go through positive cycle. It will end at some point and it will go to in negative direction or opposite direction, and again it will reach to your axis. So from point to ending point, you can consider like a period. So this is one cycle. So your signal will have one complete cycle. So if you look at this diagram, the period is 2. So this is one period, this is another period. Okay. So if you want to calculate frequency, so it is the inverse of your period. So this will give number of waves happen during a particular duration. So this is what we discussed yesterday. So each and every processor will work on some frequency. So will work on from frequency. If a processor contains the higher frequency, it will do more computation. So this is the basic logic. Okay. Next, we'll try to cover the logic level. Okay. So we need to discuss logic level before discussing digital signals. A logic level is a voltage level that represents a defined digital state. Okay, a logic level is a voltage level. Again, voltage level is physical. Voltage level is physical. So sometimes voltage could be high. The higher of 2 voltage, typically 5 voltage. So in your computer, in your laptop, in your electronics, the maximum voltage is allowed is only 5. So remember, so most of the time we'll work with 5 voltage. And the lowest voltage, okay, logic low is the lower of 2 voltage, typically 0 voltage. So these two states will define our digital logic. Okay. So this is the description. So where we are starting 0 voltage, from 0 voltage, okay, until 2 voltage, we'll consider low logic. Okay. So here it is different. Okay, 0 to 0.8, they will consider low logic, and in between 0.8 to 2 voltage, no logic is associated. So how you can understand this? Suppose if you have a signal, we'll consider this range, as logic low, and you have intermediate, you are not associating any logic, not associating. Okay, then only these two, 2 to 5 voltage, you are associating high. Okay, so what you can represent this logic low and logic high, you can map to true or false. Again, you can map to on and off. Again, you can map to 1 and 0. So this is your logic level. According to your logic level, you can represent any information or you can interpret any information. So these two belongs to binary. Value, or you can say binary states. Okay, in binary, there are only two symbols, either 0 you can represent, 1 you can represent. So how you going to map your logic level that represent your system? So you can reverse this logic also. You can keep it as low and you can keep it as high. Okay, but whenever if you're naming your logic level, it should have some meaning. So here you can notice 0 always represent low, 5 always represent high. So comparatively, you need to rename your logic design. Okay. So take an example of digital signals. Okay. So what digital signal, how to represent digital signal? Most of the time it is referred to square wave or clock signal. Okay. Their minimum value must started from 0. range to 5 voltage, and they can be periodic or non-periodic, like analog, same time. Okay, the signal of the time of that signal is high th. So whenever that signal reaches that peak, you can percentage of the period. So look at this example. Look at this example. Are you able to get the idea? So here you are starting from 0 and you are going up to 5 voltage. So each and every time your signal value varies. Your signal value varies according to timeline. So if you want to understand part of digital signal, okay, you need to have this fair idea. So in same way, you try to measure your signal from axis to the maximum peak, it will give amplitude. Okay, so this is the high time because your signal reaching the highest level. Okay, and this is where your signal reaching lowest level. So you can have the difference TH here, TL here. Again, your signal is starting to reach highest level. Again, TH. So again, TL. Okay. So this is the period. So this is similar to this. This is similar to this. Right. This is the period. So again and again, we need to remember for all digital signal, the value repeat. So this is one period and this is one period. So we have two period, T1 and T2. Okay. So next we try to count the frequency. So it is a measure of number of occurrence of the signal per second. Okay. So imagine there are two cycles. You can say two hits. You can imagine in this way. So in this case, it is two hits. Okay, two complete cycle. We discussed all this stuff. I will skip. And what is the meaning of duty cycle? It is the total ratio of TH to overall period time. Okay, so this is the ratio between T. So this is your duty cycle. So rising edge and falling edge. So this is the rising edge. Okay, this one is rising edge and this one is also rising edge. Rising edge, rising edge. Okay, because it will increase. It will increase from this point. Okay, this is falling edge. So here your signals start to fall towards your ground. So this is falling edge. This is falling edge. You want to design a digital system, you need to understand from the architecture level. You need to write programs, application to the transistor. And for that, you are using electrical signals. So what type of signal you are using? You are using discrete signal. Okay. So atomic element of digital system is binary value. So try to understand each and everything one by one. Okay. Try to understand each and everything one by one. Okay. So imagine you have a simple ideal switch. So here the electrons will flow. So here your electrons will flow. So now switch is off. Now switch is off. Off means it is not contacted with your output. Suppose if you're on, if you're switching on, it will connect between your input and output. The electrons will freely flow. The electrons will freely flow. So this is how all your computation happens in your system. So this is the basic idea about a switch. Okay. So we try to introduce digital system. We try to introduce digital system with the comparison with analog. So analog is continuous. Analog is continuous. So digital system will take only two values. either 0 or 1, or either high or low, okay, either false or true, in this way. Okay, so in this way. So analog axis to peak and peak to axis. Here the axis to top and top to axis. So all digital computer use digital system. Okay, so whatever the computer we are using, that is a digital system. Okay, that is why we call digital computer. So before digital computer, we tend to use analog computer. Okay, we gave up on analog computer and we came to digital computer. So in digital computer, what we are doing, we are giving inputs and we have digital circuits. It will compute all your tasks and it will give digital outputs. Okay, so this is the important point. Once we used analog system, the same most of the process we are using digital. Take an example of audio recording, CD, MP3. Before using our mobile phone, we have telephone system, dial, trunk and dial. Okay, so which is exactly equivalent to analog. Okay, so everything we did in analog, we slowly evolved to digital right now. So there are 8 advantages of using digital system. So one is reproducibility. So in analog, once you compute a signal, okay, you never able to identify the previous information because everything is mixed up. So analog is like continuous. Okay, there is no trace back, and you will have accuracy of result. So analog, you can't have that much of accuracy. That is why we move to digital. Third one, it is more reliable because in analog, each and every signal are prone to noise. Take an example of talking. If I am talking, so the sound wave will propagate in analog nature. Okay, it won't reach much distance. So in between, so much of noises will add on. In between is some people are speaking, is some people are doing disturbance. Each and everything will add noise to my voice signal. Okay, you can consider in this way. And comparatively, it is easy to design. Okay, to design a analog, you need very specific mathematics skills, but to design a digital, you don't need that much of mathematical skill. Very simple mathematics. Okay, and digital give flexibility and functionality. Digital will give flexibility and functionality, and you can program each and everything over digital, and you can program each and everything in digital. And you can compare speed. The digital logic element can produce an output in less than 10 nanoseconds. Less than 10 nanoseconds. In some cases, sophisticated analogs take a vast room and which is prone to error. That is why we shifted analog to digital. Okay, this is only due to the rise of integrated circuit. So if integrated circuit not evolved, still we might use analog computer. Still we might use analog computer. Okay, to understand between analog and digital and what is the number system we are using, we need to understand the decimal, binary, octal and hexadecimal. Okay, so we divided number system into 4 related to computer science. Okay, so decimal, normally what we are using into day-to-day life, we are using decimal. So decimal value is 10. Decimal value is 10, and you can see downside starting from 0 ending up to 9. So we have 10 symbols. We have 10 symbols. So in binary, base value is 2. It means you have 2 symbols. You have 2 symbols. So in octal, you have base 8. It means you have 8 symbols. Okay. In hexa, you have 16, and you are using decimal to represent. And you are using decimal to represent. You can represent only up to 10 symbols. 10 symbols. So extra, you have 6 combination. That is why you are using alphabets. Okay, so try to compare decimal and hexadecimal. Hexadecimal having 10 symbols along with 6 additional. 6 additional. So if you are representing anything in hexadecimal, okay, which is more prominent, which is more compact. Okay, so look at our fingers. So look at our fingers. So we use fingers like a computational device. We use fingers as a computational device in earlier stage. Okay, so how we are using fingers? We are starting from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 fingers. We have 10 fingers to represent 10 physical quantities. 10 physical quantities. Suppose if you want to count 11, if you want to count 11, what we'll do? We try to reuse the same finger, reuse same finger with some abstraction. So you can calculate 11 in your mind, because you know you already used all your 10 fingers. If you want to count 11, abstractly you will count through your mind. So this you'll consider 11, 12, 13, and it will keep on go. Okay, so this is how we represent physical quantity through a number system. So what is the basic of this? We are representing physical quantities through number system. So this is what we discussed, right? So before this, I tried to okay. So take an example. Take an example decimal. We are not representing binary because it is running out of symbols. Okay, running out of symbols. Why? Because binary will represent only two values. So if you want to represent binary value, sorry, decimal value 2, you need to reuse same symbols again. So what you will do? You need to add 0 plus 1, which will lead to 1. So this is called binary addition. So if we add 0 plus 1, okay, it will lead to 1. Okay, again, if you're adding 1 with 1, it will lead to 1, 0. So this is the difference you can make out of your symbols. So here you can represent 2 with the help of 1, 0. So look at here. So what we are doing, we are reusing the same symbol to represent value 2, right? So if you understand this, you can understand 3. If you want to represent value 3, you are running out of symbol. Okay, again, what you supposed to do? 1, 0 plus 1, you will add 0 plus 1 is 1, and 1 will come over here. So you can represent 1, 1. So this is the equivalent of decimal value 3. To differentiate, what we do, we try to put base like this. So this is decimal, right? So that is why I put decimal value below this. This is base. To represent binary value, I'll put 2. So this is how people would know which value represent which number system. Okay. In same way, if you want to represent value 4 in decimal, what we supposed to do? We have 11. Sorry, we have 1 1. So this is wrong representation, right? So we have 1 1 and we are adding 1. Okay. So what is the binary logic? 1 plus 1, it will give 1 0. So 0 will come over here. 1 will come like carry forward. Okay. So again, we need to add 1 1. Okay. It will go to 1 0. So here you will have value 1 0 0. So likewise, what you do, you can represent all these value. You can represent all these value. You can represent all this value until 9. So if you have pen and paper, you can work on. So 5 1 0 1. So keep on add 1 along with this. So if you're adding 1, so here 0 comes, here 1 comes. So here 1. If you're adding 1 more, 7 1 1 1. Then if you want to count 8, then what happens if you're adding 1? So 1 0 1 carry forward, 1 0 1 carry forward, 1 0 1 carry forward. So up to 9, no issue for decimal. Okay. So 1 0 0 1. So look at 10. So look at 10. So here decimal running out of symbols. Decimal number system running out of symbols. Because from 0 to 9, we have 10 symbols. Okay. From 0 to 9, we have 10 symbols, like 10 fingers. Okay. So if you are running out of fingers, what you will do? You will reuse the same finger. That is why we are reusing 0 1 combination over here. So this will represent value 10, physical quantity value 10. Okay. So one important property you need to notice. So when there is additional digit needed, additional digit needed for binary, okay, 2 power something, 2 power something. Okay. So look at here. Okay. So 2 power, again you will have a 2 power, again you will have 2 power. So until that you can easily maintain. So whenever 2 power 1 comes, you need to have some difference in your system. You will have some difference in your system. So this is how it looks like. So decimal 0 0 0 0 1, the last digit will be 1. 2, the last 2 digits will be 1 0. Second notice, you can notice. So this is single binary value. Okay, these are 2 digit binary value and these are 3 digit binary value. So we can segregate in this way. We can segregate in this way. So whenever there is a rise in 2 power something, extra digit will require. Extra digit will require. Okay. Same way you can compare with octal. So binary until 0 to 7, 8, you can represent the help of octal. Okay. So octal have 8 symbols. Octal have 8 symbols. Okay. So after 8, you cannot represent 9. So 9 is not permitted in octal. Okay. Because we have only 8 symbols, we need to reuse 1 0. We need to use 1 0. Okay. In same way, you need to go do, you cannot represent 18 and 19. Again, it will come 2 0. So this is the difference between binary, octal, and decimal. And what is the meaning of hexadecimal? You can see binary decimal value 9, you can represent with the help of 9. If you want to represent 10, so hexadecimal have more room space, more symbols hexadecimal have. Imagine one person having 16 fingers. He can count more things than you. More computation capacity he could do. In similar fashion, hexadecimal have 16 symbols. Hexadecimal have 16 symbols. To represent binary value 16, then only it will need extra digit. Then only hexadecimal will extra digit. Okay. So you can imagine in this way. So decimal value 10. Okay. Decimal value 10, which you can represent with a single letter, hexadecimal. Okay. So decimal value 16, then only it requires value 10 in hexadecimal. I hope you can understand all this simple stuff. Then we can proceed to comparison. Okay, so whatever you are writing in application software, so application software is layered over operating system. So operating system will interact with your architecture. This is hardware part. So here the software. Okay, so architecture is overall framework. From architecture you have micro architecture, because you have multiple digital components, and all these digital components working on digital logic. So here digital logic will come. So this is our today's topic. Okay, so all digital logics can be accomplished by using digital circuits. So each and every digital logic contains multiple digital circuits. Okay, so if you go in depth, okay, you are creating digital circuit with help of analog circuit. So this is very contrasting. This is very contrasting. Okay, even though it look like digital, basically each and every signal exists in this universe are analog in nature. We try to use analog signal in a discrete form. Okay, so I don't want to confuse much more, but basically whatever the signal exists in this universe, it is analog in nature. Sometimes we are manipulating analog signal, and we are using like digital signal. Okay, so have this logic, and all this analog circuit will help you, will help you to create devices. Okay, so all these devices will work based upon physics law. So basically we are able to accomplish everything with the help of electrons flow. So this is very beautiful comparison between layer by layer. Okay, so for that we need to use digital electronics. So digital electronics can represent your information. This is your binary information. This is your binary information. You can represent only two values. You can represent only two values. Okay, so that is why it is called discrete value. So you will have a distinction. So here you can notice, where we discuss that. Yes, so here you have distinction, right? We are separating, logic low and logic high with the help of threshold. So in semiconductor they call threshold voltage. They won't consider this voltage belongs to either low or neither high. So this will separate your. Okay, so no voltage means 0 voltage, and full source voltage means 5 voltage. So we are representing binary value. So this is your binary value. So everything is like abstraction. Okay, we are using physical signal to represent binary value. Okay, so exactly it is not no voltage, it is not low voltage. Physically it can vary 0 to 1 voltage. So low means not exactly low because it is continuous, it is continuous. So that is why we are keeping the range 0 to 1 like low, the range 4 to 5, the range 4 to 5 you can represent like 1, you can represent like 1. Okay, so how we going to achieve this value? By using your device like switches, by using your device like a switches. So this will help you to mimic your analog signal into discrete value. So this is how you able to attain digital signal, digital signal. Okay, so again we covered all this stuff. I will skip this. Right, suppose if you want to represent the information electronically, you can consider 4 different light bulb. Okay, if you are switching on, if you are switching on, some student is there. Okay, if you are switching 2/3, 2 students are there. If you switching the bulb to full potential, okay, 3 students are there. If no students are there, they will switch off everything. Okay, you can make the same light bulb to represent 10 different information. So according to your manipulation, you can represent n number of information, right? So again, I am iterating the same analogy. Analog electronics dealing with non-discrete value, which is continuous, which is continuous. Digital electronics deal with discrete value, discrete value in the sense 0 comma 1. So this is binary. So if you're able to separate your signal, you can represent digital logic. Okay, I'll skip all this stuff. Now we start the basics about Boolean algebra. So Boolean is a mathematician. Okay, he developed Boolean algebra. Okay, they named in the name of George Boolean. So what is the basic meaning of algebra? Algebra will contain so many integers. So it will contain so many set of elements. So you can do set of operations. Okay, so you can create postulate and axioms. So if you okay, so Boolean algebra, okay, he tried to understand the logical reasoning, the calculus of proposition. Okay, so what type of calculation? True or false, yes or no. Okay, so he tried to associate only two distinct logics. Okay, sometimes the question will be very straightforward, yes or no, true or false. Okay, accepting or rejecting. So we can map all these type of answer in the form of binary value. Okay, you can ask whether a particular animal is cat or dog, or you can ask any species belongs to animal kingdom or plant kingdom. Okay, so by representing binary value in a hierarchical level, you're able to take some decision, you're able to take some decision. Okay, you can combine both binary value and you can create more number of operation, you can create more number of operation. So this is for single, this is for single, this is combined form, this is combined form. So what it actually means, you can combine two binary value and you can make operation between them. You can take two binary value and you can make operation between them. Okay, take an example of 0 or 1, which is equal to 1. Take an example of 0 or 0, it will equal to 0. Okay, same way you can have opposite contrast in unlogic. We will cover one by one. We'll cover one by one. Okay, so if you want to implement a digital logic, you need to have some device. So this is your device. Okay, so this device will help you to implement your digital logic. A digital device or gates have one or more inputs and produce an output that is a function of current input values. Okay, so all inputs and outputs are binary. So here we are restricting each and everything belongs to only two values. Only two values. So this is our boundary. This is our boundary. So whatever the decimal value we are having, we need to convert everything into binary, and we need to feed this binary value for your device. So this is very important. This is very important. And a gate can be a combination circuit. A gate can be a combination circuit. And if you're creating n number of circuits, okay, it will form a digital circuit like a connection. One gate is connected to another gate. That gate output is connected to another gate. In similar two values belongs to binary. Okay, two level we are using. And what are the operation we can use? Multiplication. Okay, so am I audible? I'll check my internet connection. So 0.0 you'll get 0, 0.1 you'll get 0, 1.0 you'll get 0, 1.1 you'll get 1. So if both inputs are true, if both inputs are true, then only you will get true. If you're associating 0 with false, 1 with true. Okay, so look at the OR logic. 0 plus 0 you'll get 0, 0 plus 1 you'll get 1, 1 plus 0 you'll get 1, 1 plus 1 you'll get 1 0, but you need to have only one output like a decision. Like a decision. So that is why instead of 1 0 you'll get 1. If 0 is true, 1 is created so much of problem for George Boolean. So during 16th or 17th century, people cannot understand this not logic. If somebody is saying true according to Boolean not logic, this statement is true. If somebody is saying false, okay, according to not logic, this statement is false. So this is contrasting. So that is why people punished him. So in 16th or 17th century, because of proposing not logic, people punished him. But he is the foundation of all this Boolean logic. Okay, so these are the symbols. So if you want to represent all these gates, you need to have some symbols. So these are gate symbols. Okay, so here you are giving two inputs, A and B, and you have a straight line and you have a curve like D. Okay, and here you will get A dot B for and. So here you will get A. Okay, so here you will have a triangle followed by a circle, which is a knot. So if you are giving 0, here it will 1. If you are giving 1, here it will become 0. Right? In AND and NAND, you are putting a NOT gate before your AND gate. So it is like this. So if you are putting NOT gate before this, which will convert into NAND. Same way, if you are adding NOT before your NOR, okay, you will represent NOR. Okay. I don't want to waste time on this topic. You just go and understand by yourself. So this is what we discussed, truth table. So here we have inputs. So here we have outputs. So this is for AND, this is for OR. Okay. So according to your digital logic, your output will vary. According to digital logic, the output will vary. Okay. This is called truth table. So you can have n number of inputs, and according to your logic, you will get your output. So we discussed about AND gate, right? We discussed about AND gate. If you have multiple AND gates, you can form a IC. If you have multiple AND gates, and you can form a IC. So this IC contains 4 AND gates. This IC contains 4 AND gates. Okay. So likewise, you can create n number of gates to form a chip, IC chip. So this is a OR gate, and this is the family TTL74LS. So it contains 4 OR gates. So likewise, you can combine more number of gates. You can do more number of OR operation. More number of OR operation. So this is the example of combining 4 NAND gates. So here there is a twist. You can implement any gate. You can implement any gate with the help of NAND gate. NAND gate. Okay. So you can implement AND gate, OR gate, NOT gate by using a NAND gate. So this gate is called universal gate. Okay. So even though we are discussing all these gate combination, but NAND gate is more powerful. Whatever AND gate do, you can implement by using a NAND gate. Whatever. So you technically everything is based upon NAND gate. Same way, you can use NOR gate alternatively. So NOR gate is also universal gate. Okay, so XOR gate. So if you have a circuit, you need to draw in a specific way. So if a Boolean is provided, we can easily draw a logic circuit. So take an example of F1 equal to X, Y, Z1. So take an example of X, Y. Okay. So what is the meaning of XY? It is multiplication. So which gate you will pick? Which gate you will pick? You will pick AND gate. Why AND gate? AND gate will do A dot B. Okay. So that is why we got AND gate for XY. We got AND gate for XY. Okay. So what is the meaning of Z dash? Z dash is negotiation of Z. Inverse. You can say inverse. Okay. So how will you produce inverse? By using a NOT gate. By using NOT gate. Okay. So look at this. So X dot Y achieved by AND gate. Okay. So this output is combined and multiplied with Z dash. Okay. So technically you can see X dot Y dot Z dash. To attain Z dash, we use NOT gate. So I'll put in this way. So Z, we implemented NOT gate. For this, we AND gate. Okay. For whole sum, we implemented AND gate. So this AND gate has 3 inputs. This AND gate contains 3 inputs. Multiplication of 3 variables. Okay, which will lead to F1. So try to analyze logic gate to express F4. So what we suppose, we are using AND gate. So AND gate will multiply A dash dot B dash. Okay, and we are passing through OR gate. What OR gate will do? It will do addition. It will do addition. So A dash dot B dash plus C, and we are passing through NOT gate, which will take inverse of everything. So I can imagine in this way. So inverse of everything. So this is equal to this. By choosing proper gate, we can achieve proper logic design. This is the idea. So I'll skip this and I try to show demo. Okay. So I will share this link for you. So here you can work all logic gates along with you. I'll put in chat box. So where to put in chat box? Can anybody put message so that I can see chat box? Okay, thank you, thank you. So go to this website. Go to this website. Whether my link visible? So click this. Click this. So you can go to virtual lab. So all IIT, NIT, they have this lab, virtual lab. So click the first one, verification and interpretation of truth tables. So if you are teaching this course, it will be very useful for you. So no need to use board. So you can save some time. So click simulation, click ungate, click ungate. And you will have this view. Maybe I will zoom it. Okay. The first thing what you're supposed to do, you need to click battery. So click battery over here. It is get connected. Okay. So do this. So every one of you. So click this battery, make connection to your circuit. And this is switch 1, switch 2, switch 3. And we are implementing AND gate. Okay. So power supply starting from plus, it will go to switch. So you need to switch on. Now switch is on. It is ready. The power supply will go here. You can see the green color. Green color. It will reach until the switch 2 and switch 3. So here we have resistor. We have transistor Q1. Downside we have one resistor. We have transistor. And downside we have resistor. One more resistor which is connected to LED light. So what is the logic of AND gate? I will use open board. Wait a second. So what is the table of AND gate? So X, Y, output. Okay, you can consider off. Okay, off means 0. Okay, this switch is off. This switch is also off. Off means 0, 0. What is the output? LED is not glowing. This is also off, 0. Okay, so what you do, click one of that switch and make it as on. Now what we are doing, we are switching on. So one of the switch is on means 1. Okay. The one more switch is off means 0. What is the output of your LED? Already in off state. Okay, so what do you do? You switch off this device. So now this is off. and this is on. This is on. So the first switch is off now. Off means 0. The second switch is on. On means 1. And what is the output you got? Off. So this is about your LED. Okay. So look at the last combination. Look at the last combination. So here you switch off both switch. You switch off both switch. On. Finally, the LED is also on. It will glow. So what happens? I try to, okay. I try to move here. No, not possible. Okay, I'll write over here. I hope so everybody can understand. On, on. This is also on. So this is the final stage. Only if you give true, multiplied with true, equal to true. So likewise, you can execute all these logic circuit one by one by yourself. Okay. So go here, go here, go here, click simulation, click OR gate and do by yourself. So you can give truth table. You can ask your students to verify whether it is properly working or not by changing your switches. So if you're teaching some tools, some topics with interactive tool, so it will go easily. It will go easily. So first we need to connect battery. Okay. So verbally I will tell because you know the OR logic. Now we are switching on. So 0 plus 1. Okay. So this is 0 off. Switch is on 1. So 0 plus 1 which is equal to 1. Okay. Next time switching off and second switch. Again 1 plus 0 which will equal to 1. Okay. So 1 plus 1 is also 1. So this is OR logic. The last one I want to demonstrate, NOT logic. So this is very easy for us, for students also. So we have one switch, we are giving power supply. Okay, LED is on. Okay, so one means on, and if you act this switch, it will switch off. So these two switch will act like toggle, right? So switch on, switch off, switch on, switch off. So opposite for your state, opposite for your state. Okay, so this switch will act like NOT gate. So switch 2 will act like NOT gate. Okay, so again come back to slide. So what we discussed about analog signal, digital signal, and we discussed about digital system. To represent digital system, we are using Boolean logic or binary logic, and we came through some fundamental gates. Now we are about to see flip-flops, we are about to see PLD, FPGA, which is very latest. Okay, so how will you represent digital information in electronic device? So this is the first question we need to ask. So for that, the answer is by discrete voltages. So if you are separating voltages, you can represent your information. Okay, so what is the basic digital element in electronics? Nothing but a switch. So you can consider all these gates will act like switch. Either it will allow or it won't allow electron flow. So this is basic. So if you want to represent a digital information, you can use a physical device like a switch. So you can see over here, this is one switch, this is one switch, right? Same way you can have multiple switches to represent your digital logic. So this is a digital abstraction. So it is difficult to make ideal switches, which means a switch is completely on or completely off. By making a digital abstraction, we are achieving it. Okay. Because we are imposing some rules that will allow analog behavior will be ignored in most cases. So that is why we are able to attain the digital abstraction. Okay. It's an example of digital switch. So here you have series of switches. This is unknown origin. And each and every time if you design new processor, this logic voltages will keep on decreasing. So that is the beauty. That is the beauty. So to avoid the noise margin, we need to decrease digital logic, voltage logic. So this is an example of MOS transistor. Okay, this is the example. So you can go and study. And this is about CMOS inverter. So if you want to invert something, you can use CMOS technology. So you can see number of logic gates. So this is an example of switch model. Okay. So a flip-flop, either it will store 0 or 1. So it is like a device, like a transistor. Okay. So it will store at particular point of time, which is written by clock input. So according to your clock input, okay, it could store some value or it can change that value information. Okay. By using flip-flops, you are able to create a sequential circuit. So one circuit followed by another circuit, followed by another circuit, it can form sequential circuit. And these are the example flip-flops. These are the examples of flip-flops. I hope I am audible. Am I audible? Is my screen is visible? Okay, great. So these are basic flip-flops. So I don't want to discuss more. Okay. So if you are designing small gates, if you are integrating more number of gates in sequential manner, we are able to achieve integrated circuits. So it is a collection of one or more gates fabricated on a single silicon chip, which is called integrated gates. Okay. So if you're looking at smartwatch, it will contain less number of gates. But if you're looking at a processor, it will contain more number of gates. Okay. Take an example of Intel i9 processor, which will contain millions of transistors. Millions of transistors. Okay. So if you keep on increasing your devices, you can scale a very large digital circuit. So this is the meaning. Okay. So all your devices, AND gate, NOT gate, NAND gate are embedded over here. All digital gates, what we discussed. Okay. They try to put in this IC like a fabrication. So somewhere you will give power supply. Okay. Somewhere you will give ground. So this will make the entire circuit to work on. Electrical circuit, you can imagine. Okay. And more number of gates, If you are putting in a single IC, you are having a powerful processor. So what we discussed, VCC for voltage power supply, GND for ground. So this is for NAND gate. This is for so this is for NOR. Okay, this is for XNOR, right? So likewise, we have multiple varieties of gates. And you can make a programmable logic devices. So this will allow the user to program when they are manufacturing. Okay, the complex PLD is the form of simple PLDs on the same chip. Okay, if you are making a programmable logic chip, okay, which is called field programmable gateways. Okay, so many varieties of chips are available. So according to the manufacturing, according to the sequence, you can create n number of varieties over your chip. Okay, so you can create chip for single function, or you can create a chip for multiple function. Okay, so sometimes if you are looking at your fridge, okay, if you are looking at your fridge or smart TV, it is purposefully built for a particular function. Okay, so if you use CPU, you can use it for n number of tasks, so which is general purpose. So this is an example. Your CPU can do multiple function, multiple tasks when compared to a smartwatch, when compared to a smart TV. So they have some restriction. Okay, smart TV have some restriction, or smart fridge have some restriction. But your CPU is general purpose device, a general purpose processor. Okay, so this is an example. Okay, so each and everything will follow some particular application or size or preference. So based upon that, you can do, take an example of an Arduino or Raspberry Pi. So these are only at smaller level. So when you compare to your CPU, this is built for specific purpose. So more rules and regulatory boundaries are there. But when you compare in power, this will consume more. So power is much more higher over here, power consumption. Okay. So here power consumption is very low. So, okay. So you can design your IC according to the situation, according to the application. So this is one more beauty, right? So with the help of printed circuit boards, that image for you, printed circuit board. So notice this, if you open any electronic gadgets, so they will print in this way. So I try to open. This is one IC, this is one IC. Each IC contains number of digital logic gates, whatever we discussed. Okay, so it will contain millions of transistor, millions of AND gates, OR gates, NOR gates. Okay, so here the power supply will go. So you can see this pathway. So here each and everything you can consider like a wire. Okay, everything they integrated, they printed in a circuit. So this circuit will give a platform for them. So you can imagine the entire circuit in your house is printed in this way, which is very, very neat and tiny, and won't move out. So this is the idea of printed circuit board. Okay. So why we need to understand digital design? Because if you want to create any software, you need to understand digital design. If you don't know your device, you cannot create efficient software. Okay, so before developing any before releasing any software, they will test with multiple hardware. So this is the reason the engineer who are developer, they need a digital logic verification. So some engineers are there, they will test your software in multiple systems, multiple variety of systems. So it should be work for IoT, it should be work for normal PC, it should be work for server. Okay, so this architecture will vary, and they need to analyze how performance vary along with your software. Okay, the same software you cannot use for your CPU, you cannot use for your mobile. Okay, the software version will definitely vary. So take an example of WhatsApp. So whatever you are using WhatsApp in your laptop will not have the same specification for your mobile. So this will vary, right? Even though they have same purpose, but architecturally they need to design in different logic. Okay, so if you are designing any hardware, you need to design in the low level of design of physics and IC manufacturing. So you need to design a transistor from basic level. So this will give you a added advantage. So you can see difference between Intel and AMD. Okay, mostly Intel will be used for general purpose. General purpose. AMD they will use for graphical purpose. Okay, so in initial days in Hollywood movies, so 90% of the movie they will go for AMD processor instead of Intel because it is cost effective, and much more it will give throughput when compared to graphics. Okay, now Nvidia comes, they are developing a GPU which is dedicatedly for graphical processing unit. So initial days people choose to prefer AMD. Nowadays the people try to prefer Nvidia. So by conquering some technology, you can easily able to conquer the entire market. So you can change the scenario. So which is very, very dynamic. Okay. If you're able to serve the purpose in efficient way with less power, people will go for that. So I don't want to discuss so much. I already discussed. So this is how you can see your program in very large scale. Okay. So which is called VHDL. So if people go for high level processor or sophisticated processor, they will use this tool. So if you want to know, you can contact EC people or EEE people. Okay, they will work on this software. So this is called Verilog. Now uh, we came to time. We try to relate how these gates related to quantum and why we need to study digital logics to understand quantum logic. Okay. So what we discussed, classical digital logic gates will act like real gate. So this will allow electrons flow or not. Okay. So each and every, yes, it is integrated. Sometimes they will combine uh, graphic card or GPU along with your processor, but people won't normally okay. I use due to this mismatch. It could be want to skip you. Very good question. Okay. So uh, I'm audible, I think so. That is why people are responding. So if you are validating one or two statements at each and every gate, you will get some output. So take an example of AND gate or gate NAND gate. Okay, if that input satisfy that gate logic, if that input combination satisfy that gate logic, it will allow, otherwise it won't allow. Okay, so we discussed AND gate, OR gate, NOT gate. So look at the definition. If both statements are true, then you will get output as true. If one of the statement is true, you will get output as true. So this will negotiate or opposite the given statement. So 0 means 1, 1 means 0. Totally opposite, like an enemy, which will always oppose. Okay. Similarly, in quantum we have logic gates, which is called quantum logic gates. Okay, logic is important. How we are connecting the physical quantity in your system, that is called logic gates. Okay, so qubits obeys rules in an algorithm, and these rules are called gates. So you need to create a rule and you need to abstract in a gate form. Okay, so these gates are applied one or more qubits at a time. Okay, when a qubit is there, you can apply multiple gates over that. So these make qubits to move around the block sphere. Okay, so each and every time if you do all this operation, your quantum state position will keep on changing. Okay, so these changes will reflect in amplitudes, which will affect outcome of the qubits. Okay, take an example of bit flip, which is exactly like NOT gate. Take an example of phase flip, which will change sign of your quantum state. Okay, so take an example of Hadamard, which will create equal superposition. Take an example of control knot, which will flip one of the qubit state. So this is good if you know how this gate works. So even though these topics we never covered, I want to give you a glimpse. So I will share one link with you in the chat box. Can anybody put some message? I can see his chat box over there. Yes, thank you. So go to this website. Please go to this website. I hope the link is visible. Okay. So whatever I do, you please repeat. I will give some time for participants. So these two are, yeah, I already shared. Please check in the chat box. Where to see chat box? Yeah, once again I will share. Please look at this chat box. Go to this link. So these two are pure quantum states. Pure quantum states. Okay, which is equivalent to binary value. Which is equivalent to binary value. So stage 0 representing binary value 0. State 1 representing binary value 1. So imagine in this way. Okay. So we are mapping binary logic. We are mapping we are mapping binary value to quantum bit. Okay. Why it is quantum bit? Bit stands for binary. Bit stands for binary. So that is why state 0, state 1 are called pure states. Okay. So I am in state 1, state 0. So state 0 in North Pole, state 0 in North Pole, and state 1 in South Pole. So how we are dividing this North South Pole? By using equator. So this is your equator. Okay. So what we are doing, we are representing this whole hemisphere, northern hemisphere for state 0. We are representing the whole southern hemisphere for state 1. On what is the extreme point? North Pole and South Pole. So this is the idea. Okay. Now we are clicking X gate. X gate is nothing but NOT gate. So X gate is Pauli X gate, which is nothing but NOT gate equivalent. This is NOT gate equivalent. So in classical, what we say, NOT gate. In quantum, what we say, Pauli X gate. So note down, Pauli X gate. Okay. Now we are pointing to stage 0. If you click X gate over here, it will go to stage 0. Sorry, state 1. So it is in stage 0. We are clicking stage 0. So click X, it will move to state 1. Are you able to see change happen? So from here to here, are you able to see? So next what you do, from state 1, if you apply X gate, it will move to state 0. So this is we give 0, it will give 1. If we give 1, it will give 0. The same thing Pauli X gate will do. So X gate is bit flip. X gate is bit flip gate. So X gate is bit flip gate. So what we do? We apply X gate in state 1 and observe it will go back to stage 0. So if you apply 2X gate, next to next will cancel each other. Take an example. Suppose if you have a NOT gate, okay, followed by one more NOT gate. So what do? You try to give the input. You are giving value 0. And what you will get after this NOT gate? You will get value 1. Then after this NOT gate, what you will get? Value 0. So applying 2X gate will cancel each other, which will go back to original state. So this is exactly happened in X gate. If you apply 2X gate, it will cancel each other. Okay. So look at this same scenario. So we have NOT gate followed by one more NOT gate. Okay. So this time you're starting with 1. So after the first NOT gate, what you'll get? You'll get 0. After the second NOT gate, what you'll get? You'll get value 1. So applying 2 X gate will cancel each other, which will go back to original state. I hope everybody able to follow. What happened? Okay, good. So it means X gate has its own inverse. Okay, so it is like a mirror. So X gate have its own opponent, which is equal. So whatever the first gate will do, the second X gate will cancel it. So you can imagine in this way. So if you are adding a wave in this direction, and if you are adding the same wave which is opposite direction, which will nullify each other. So adding 5 plus minus 5, which will equal to 0, which will nullify. Okay. The second gate we are about to cover is Y gate. So this is Y gate. Okay. We start from stage 0. So click Y gate from 0 and observe what happens. Click stage 0. Click Y. Observe what happens. It will go back to state 1. So it will go back to state 1. So which is similar to X gate. But if you notice downside, you can see addition of pi rotation. Okay. So Y gate will do bit flip along with pi by 2 phase flip. So physically you cannot see any change, but downside you can see this phase flip. And what is the value? Pi by 2. Okay. So what you do? Stage 0, apply Y gate, it will go back to state 1, but pi by 2 rotations. So this is the difference. So X gate, stage 0, which will go to state 1. So there is no additional phase rotation. So this will give some freedom for you. So Y gate will have some freedom. We can represent more information or variety within your NOT operation. So classically, you cannot have this difference, right? You cannot change phase. You can do only bit flip. So this is some advanced model of X gate. You can consider NOT gate. Are you able to get the flow? So stage 0, apply Y, it will go to state 1 plus pi by 2. Okay. So apply Y gate over here, it will go to stage 0. So very easy. So click stage 0, So all of you click stage 0, click Y gate. Downside you are able to see phase pi by 2. Okay. So click Y from state 1, you will go back to stage 0. So click stage 0, click X, observe where it goes, phase equal to 0. So no change in your phase. In X, you can see no change in your phase. So again click X, it will go back to state 1. Even though X and Y will do same operation, but Y will have some additional advantage by changing phase flip. Are you able to get the idea? Instead of using a single color, you can mix some different color and you will get new combination. So Y will have a new combination. Phase sine versus cosine. So what is the difference between sine and cosine? Only the phase. Only the phase. You can see phase difference, right? So this is what phase difference means. Even though it appears like same signal, it contains some difference. Difference in the terms of phase. Okay. So next we try to cover Z gate. We try to cover Z gate. So click stage 0, click stage 0, click Z gate and observe what happens. So we are in stage 0. We apply Z gate. Nothing happens. Nothing happens. It means state is retained. State is retained. So it is like pause button. Suppose if you want to do nothing, what you can choose? You can choose Z gate. Okay. So this is the idea about Z gate in stage 0. Now what you do? Click state 1. Click state 1. Apply Z gate and observe what happens. So you are in state 1. Apply Z gate. Observe what happens. So state remains same. State remains same. But you can see phase difference of pi, which is nothing but opposite side. Opposite side. So opposite side you can denote with negative sign. Okay. So from minus one state, if you apply Z gate, it will go to state 1. So click here. So click here, apply Z gate. Now it is in minus. What happens? It will come to 0. So it will introduce one more pi rotation if we apply from state minus 1. Okay. Applying 2 Z gate, next to next will cancel each other, which will go back to original state. Which will go back to original state. Are you able to get the idea? So I will summarize. So stage 0, if you apply Z gate, the state will remain. Okay. From state 1, if you apply Z gate, it will go to negative. It will go to opposite side. So Z gate will not operate in stage 0. Z gate will not operate in stage 0. So remember and point down. So anywhere in your Q sphere, it will work except stage 0. Z gate will not change pi rotation except stage 0. Okay. Question. So we try to compare one by one. Yes, we try to compare one by one. Okay. So if we apply X gate in stage 0, what happens? It will go to state 1, which is equivalent to NOT gate. This is equivalent to NOT gate. So if you apply Y gate in stage 0, it will go to state 1 plus pi by 2. So this is like NOT gate plus pi by 2 rotations. Okay. So Z gate, if you apply in stage 0, it will retain the same state to do nothing. Okay. If you want to do nothing, it is pause. Okay. So everywhere in your Q sphere, if you apply Z gate to state 1, what will do? It will introduce change in your phase. So this is change in your phase, in your signal phase. So this is like difference between sine wave and cos wave. Sine wave and cos wave, they have some difference, right? So if you want to introduce some phase difference, you can select Z gate. So you can see the difference. Y and Z have some different purpose. So according to the purpose, you need to select gate. So if you want to multiply, you will select AND gate. Okay. So if you want to add, what you'll do, you will select OR gate. If you want to negotiate, what you'll do, you'll select NOT gate. Are you able to get the logic? So depends upon the purpose, you need to select gates. Is it clear? So try to compare each and every gate slowly. Try to compare each and every gate slowly. Okay. So next, click stage 0, click stage 0, click Hadamard gate. Click stage 0, click Hadamard gate. I try to write over here. So click stage 0, click stage 0, just click over here. I already shared the link. Observe here, observe in this window. Okay. And switch over to your website. So where it will go? So look at here. So it is x-axis. It is in positive state. So these are logic gates, right? X is one logic, Y is one logic, Z is one logic. So these logic gates we are using, which are called quantum logic gates. So how digital logic gates work? It will work in the same way, but it will have additional degree of freedom, additional degree of operation. So you can imagine, okay, here you have digital logic gates, it will do some operation, but quantum is like superset. So quantum is like superset. So what NOT gate will do, X gate will do, Y gate will do, but Y gate have some more capacity. Are you able to identify? Y gate will have some more capacity where normal digital gate don't have. Is that clear, your question? So to understand quantum gates, we need to understand digital gates. Great, thank you. Okay, so we discussed stage 0. So after that, click Hadamard. Where it goes, it will go to positive state, which is nothing but it will create equal superposition. Equal superposition. So why it is equal superposition? Because it is in equator. So any point in your equator, it is away from 0, 50%, away from state 1, 50%. So that is why Hadamard gate will create equals. So if we state, so this logic so in class cannot create superposition. So that is why we need to understand the classical logic gates in order to understand what are the advantages we have in quantum. Okay, without understanding classical, we cannot use quantum in full. Okay, so Hadamard gate, no equivalent available in classical. You cannot explain in classical logic gates. Okay, you can represent 0 or you can represent 1. You cannot represent any in between value. In quantum, it is possible. In quantum, anything between 0 and 1, you have to represent. So in classical, it is discrete. It is discrete. Okay, distinguished by threshold voltage. We already covered, right? So in quantum, we don't have such kind of thing. So that is why it will give more degree of freedom. Okay. So what we discussed, from stage 0, if you apply Hadamard, it will go to positive. From positive, if you apply Hadamard, where it will go? Check your website. So click Hadamard from here and observe where it goes. Anybody having answer? So click, yes, stage 0. So click Hadamard from positive, it will go to I said Hadamard, not Z gate. So somewhat you missed. So click stage 0. Click stage 0 means click here. So I'll show pointer if you don't know. So click here, please. This is click stage 0. So click state 1 means you need to click here. Okay. So next what you do, click state 1. Click state 1. Now you can see downside. So state 1, if you apply Hadamard, what happens? Where it goes? So try to click Hadamard over here and tell me where it goes. Negative. Are you able to get the answer? From state 1, if you apply Hadamard gate, it will go to negative state in x-axis. Okay. From negative, if you apply Hadamard, where it goes? From negative, if you apply Hadamard, where it goes? Okay, state 1. So now it is in negative. If I am clicking Hadamard, it will go back to state 1. It will go back to state 1. So applying 2 Hadamard gate will cancel each other. Will cancel each other. So these 4 gates have its own inverse. Own inverse. So that is why these gates are reversible. So X, Y, Z gates are reversible. Y, Z, Hadamard are reversible in nature. Reversible in nature. Because if you apply twice, it will go back to original state. What you can do reversible computation. Reversible computation. Take an back propagation. Back propagation. Okay. So if you want to step back, you can use these gates. So in machine learning, okay. So all this stuff, we are using this back propagation. I will tell you one good example. Take an example of AND gate. So this is your AND gate. Okay. So what is the input? A and B. What is the output? C. Okay. So A, B, C. So 0, 0 means what is the value? 0, 0 means what is the value? In AND gate, 0. 0, 1 means 0. 1, 0 means 0. 1, 1 means 1. If I give input combination, can you predict output? Can you predict output? If I'm giving input, are you able to predict the output in none? Possible. Possible. Okay. If I'm giving output, can you predict input? The answer is no. The answer is no. Because AND gate is irreversible. For all these three states, you have same output. Okay, only one combination you have unique output. Why? Because we have two inputs and we are producing one output. This makes a problem. So classical gates having this problem because we have n number of inputs and we have less number of outputs. Once you do process, you will lose input combination. Once you lose your input, once you do process, you will have input combination. You will lose input combination. Okay. So same example. So look at here. Take an example of NOT gate. So what is the input? What is the output? If I'm giving 0, the output is 1. If I'm giving 1, the output is 0. So these two combinations are differentiable. If it is differentiable, the output is predictable. The input is predictable or reversible. So this is not reversible. So here we are retaining 1:1. Here we are retaining 1:1. So what is the general rule? If you are maintaining n:n, we can able to produce reversible computing. So that is why we need to study digital logics. Then slowly we need to study quantum logics. Then we can have a better idea. So you can create your own quantum gates. So we will cover S gate, T gate in upcoming session. I hope I gave a very glimpse about this quantum logics. So within this, I try to stop my sharing. Thank you all for patiently listening. So within 2 hours covering digital logics is very, very challenging. So it is entire course. I will share these notes. Don't worry. Think too much. Go there, right? Triple E, they can explain you. So people from EC, CS and E, please bear with me. Very, very basic. So nothing to do. Yes, I will share. I will share yesterday notes also.